Okay, so we're going to talk about sampling distribution model for proportions, and then after that we'll talk about another one about means. Now, we have some new variables here. This is our mean of a population. It's known as mu, right? And this p with a hat on it refers to a proportion, so that means we're referring to a proportion, okay? And what this is saying is the mean of our proportion is directly equal to the proportion percentage of success. That's what our P is, okay? That might seem weird, but I'm going to relate it to our question. The standard deviation of the proportion, that's what P hat stands for, is calculated by finding the square root of P, which is the successes, multiplied by Q, which is the failures, divided by the number of people in a trial. What the heck does that all that mean? Okay, so here's a question. It says it is believed that nearsightedness affects about 12% of all children. So if we're testing for nearsightedness, and nearsightedness is a success, we call it, okay? I'm sure we wouldn't consider it successful, but that's considered a success in our study. What that means is this is the probability of getting a success is 12% when looking through a group of children. Okay, you have a 12% likelihood of a kid being nearsighted. That would be a success. In other words, our P in this question, okay, which is going to be our kind of mean for the population, is equal to 12%. Okay, so that would be a success. Well, Q stands for failures. And since we're talking about percentages, Q is equal to 1 minus P. In other words, not being nearsighted. The complete opposite of that. That would be considered a failure to this test. So not being nearsighted. Well, in that case, what we do is we turn our percentage into a decimal. So Q is calculated by 1 subtract 0.12, okay, which is equal to 0.88. In other words, Q is equal to 88%, right? Which would be the opposite. If 12% of children are nearsighted, that must mean 88% are not nearsighted. That's what our Q stands for in this case, okay? So I'm just going to underline that. So Q is 88, which we will need, and P is 12. And it says here in the question that a school district has registered 170 incoming kindergarten children, okay? That is going to be our N in this study. Okay, so in this sample, we have 170 kids. So N is equal to 170. So already we have enough information with proportions to solve for standard deviation. And we already know the average, or the mean of the proportion. The mean of the proportion, is P. In this case, that's 12%. Okay, so that's what the proportion means. So the very first thing is, we have to do a couple of things to make sure this is a proper model. Now, the question says they want us to sketch and label a sampling model. We have to make sure we have enough information for a model, and there's a few things we have to check with every one of our studies. Okay, the first thing is called the independence assumption. Okay, and the independent assumption talks about that the samples in the study must be independent random draws of a population assumption. So what does that mean? They have to be independent random draws. Okay, well, let's talk about the 170 incoming kindergarten students. Can we assume that they're randomly chosen, these kindergarten students? Is it fair to say that it's probably just a variety of kids living in the area, and that they might represent probably the population at large? Or do you think that these, for instance, an example where this wouldn't be an independent assumption is where maybe this is a specific school for nearsighted kids. Right. Well, if we're taking a population of that, obviously all the kids are going to be nearsighted. So that wouldn't be independent. But we're just assuming this is a normal public school. So yeah, we can assume that the independence assumption is correct. We can check for it. Okay, so we assume that this is a random draw. Okay, so random. This is a random sample. That's acceptable for our study. Okay, and the randomized condition The other thing of independence is we also assume that, because one kid is nearsighted, it doesn't mean that the other kid has to be not nearsighted. Right? One kid's nearsightedness doesn't affect the other, and that's part of the independence assumption, that the two events are independent. And the second thing is, the random. I kind of talked about the random one instead. The next one is random assumption. Okay? And the random assumption is that we can assume that unless it's a school for nearsighted kids, that they're all pretty much randomly chosen, right? So independence is fair. One kid being nearsighted doesn't affect the other kid. And we assume it's random. It's just a normal public school. There's something called the 10% condition. Okay? And the 10% condition says that when we're sampling, let me see if I got it here. Yes, the sample size n, okay, can be no larger. So I'm going to say no larger than 10% of the population. Okay? So in other words, we have to make sure that the sample size, our n, which is 170 in this case, is no larger than 10%. Okay? Well, what is the population? We're talking about what here?
All children.
All children. Is it probably fair to assume that 170 kids is not 10% of all children in the world?
No. Yes.
Yes. Yeah, so it's fair to say that this is under 10%, right? We got 7 billion people in the world. Even if it's only a seventh are children, you're still looking at 1 billion people. So we're clearly under 10.
Right.
Okay, so that's fair too. So we've checked off our first thing, independence assumption. Second is random assumption, random sample. The third one is the 10% rule, or 10% condition. And then the third one is we got to make sure that our success and failures condition. I'm going to write this success. We'll call this number 4. Success and failure. The success and failure condition. And what it says is, with our successes and our failures, we take our percentages. So a success, which was P in this case, was what percent?
12.
12. So 12% to be nearsighted, which means Q, the failures,
was 88.
Was 88. We have to make sure that with our total sample of 170 kids, okay, remember n was equal to 170, that the successes and the failures are at least 10. So they have to be greater than or equal to 10 in total. Greater than and equal to 10. Okay, so, sorry, this is less than. I wrote those signs backwards. So what does that mean? What that means is we take our percentage. We need to have from our sample 12%, is that's what we're going for. Our sample size needs to be large enough that at least 10 people will be successfully nearsighted and at least 10 people will not successfully be nearsighted according to our percentages. So the way we calculate this is we take 170 and multiply by our 12%, okay, which is 170 times 0.12. And what is that value?
20.4.
20.4. Is it larger than 10?
Yes.
Yes, it is. So that means we've fulfilled our success criteria. We have to just get a number larger than 10. We have to make sure there's going to be at least more than 10 successes. Okay? And then we do the same thing. So that will, I say that was with P. And now with Q, same idea, 170 times 88%. That's pretty obvious. Is this number going to be greater than 10?
Oh, yeah.
Oh, yeah, for sure. And what is this number going to be in this case?
Oh.
That's okay. Probably around 150, 140.
Equals
149. Oops. 149.6. 49.6. Okay, so we will get more than 10 failures. Good. Those are all of our checks, which allow us to now make a model. So there's already quite a few things we had to do. Okay, very first thing, we had to make sure the independence assumption was fulfilled. Random assumption, is this a random representation of the population? 10%, make sure that we're not taking more than 10% of the population, and it fulfills our successes and failures, that we're going to get at least 10 successes and at least 10 failures. That's the very first step before we can even start to do a study now. Okay? So now that we know we have the correct amount of information to do this, what we're going to do is we're going to go about calculating our standard deviation and our mean. Okay? And what this is there's a rule of central tendencies here. Because this is an average, right? 170 incoming kids. We're going for the future here. We're assuming that the average of these kids will fall in this range of 12% because we've met all those other criteria. So what's going to happen is we're doing proportions. Over large proportions, we're going to get a normal distribution. Okay? So we're going to, again, create a normal distribution when we go through this. Okay? So let's do a bit of our calculating. We knew the average of the proportion is essentially P, which in this case is 12%. Okay? And the standard deviation of the proportion, okay, is equal to the square root of P times Q divided by N. Okay?
Oh,
So we got to actually go about calculating that. Okay? So we look for the square root of P was
12.
0.12. We put it as a decimal, right? Q,
88.
yeah, 0.88.
Over 170.
Aha, exactly. Over 170. And that'll help us calculate our standard deviation. So our standard deviation in this case, maybe you get your calculator, help me out here. 0.12 times 0.88 divide 170. I think I can square root that value. Yeah, I get 0.025. I'm going to round it to approximately, okay? So approximately 0.025, which is what as a percent?
0 or 25?
25, but
Oh, 0. Oh, 2.5. Well,
2.5%. So what it's saying is our standard deviation is 2.5%. So let's create our normal model that we're used to doing from before. We have our line, and our proportion is our mean. Remember that mu letter here stands for our mean of the population. Okay? So that's going to be our middle value. So our middle value is going to be that 12%, right? Right down the middle. I'll do my best to draw this now.
Are you packing a dinner?
Oh, yeah. So we've drawn this. Each standard deviation is going to be 2.5%. So a standard deviation to the right one and to the left one, right? And we know that we're adding one standard deviation or subtracting one standard deviation. So what are these percentages going to be? Well, this is going to be 12 plus 2.5, so this is going to be 14.5%, right? And to the left, we're going to have 9.5%. Two standard deviations is going to be 17%. That's going to be two standard deviations. Or, in this case, 7%. And finally, three standard deviations, which we know all information is going to be between, is going to be 19.5%. And what is that? 4.5? 4.5% for 3. So negative 3 standard deviations, negative 2 standard deviations, plus 2 and plus 3. Okay? So this is our model. This was the answer to question 1. We've created our model here. We have our 12% in the middle, and we have all of our standard deviations. We had to verify with all those numbers before that we were allowed to create this model, to create a normal distribution. Once we verified everything, we were allowed to create this. We say that this is representative. So for a lot of info, that's just number 1, sketch and label a sampling model. Second one is, what is the likelihood that 25 children will be nearsighted? Okay, 25 children. Well, they haven't given us a percent, so we don't know where that falls in this area. So we have to turn 25 children into a percent. Okay, so this will be our B. Well, we got to find out what percentage of the total 170 kids 25 is. So we divide those values. Okay, 25 divide 170 is 14.7. Okay, So we're going to say 14.7%. Well, we know that that is going to fall in here. And it looks like it'll fall, I'll draw like a red line for it, just outside of 1 standard deviation to the right. That's where 14.7 will probably be. Does that make sense to you?
Mm-hmm.
Okay. So now what we do is our z-score formula to find out the exact amount. Okay. So our z-score formula, we'll write it out here, is we take the proportion and we subtract the mean. Okay, so we take our proportion here and we subtract the proportion mean over the standard deviation of the proportion. Okay, now it looks very different, but really all that was before is we took the data x1, subtract our mean of x bar divided by our standard deviation, which I think they used to represent as that. It's the exact same idea. The only difference is we're using different letters to represent it.
Oh.
So this x hat, or sorry, this proportion hat here, our proportion is 14.7. Okay, so our z-score is 14.7. Subtract p. P is the average proportion, which was our 12. So we take 12 and we divide it by the standard deviation. Well, the standard deviation in this case was 2.5, right? The 2.5%. So our z-score, we're going to calculate it now. Our z-score is 14.7 minus 12, divide 2.5, 1.08. Oh, that makes sense as a standard deviation, right? One standard deviation was 14.5, so 14.7 is a little greater than 1.08. So we looked that up in our z-score table. Pink one. We looked that up in our z-score table. Maybe you'll be faster at it than I will. And I'm just going to create the table while you're looking it up, just to get an idea here. Okay. Zero.
Wait, oh no, I looked over wrong. Did I look up?
No, I think you did the right one.
Right here?
0.8599? Yep, that's right. 0.8599. That's where 1.08 is, okay? What is that as a percentage? That is pretty much 86%. Does that make sense?
Yeah.
What's the probability that, 25, I want to say that 25 or more, or more children will have nearsighted. Well, does it make sense that it's an 85% likelihood? That was a pretty high percentage. Remember, our average was 12.
Oh, wait.
Our z-score talks about everything to the left. But the question asked us, what is the likelihood that we have 25 or more? So we have to calculate we have to subtract from what value?
1.
1 or 100%. So really the true answer is 100% minus our 86%. And that's going to give us this amount, which is going to be a 14% likelihood. Okay? So there's a 14% likelihood that the kids coming in, that there'll be more than 25 of them out of the 170 will be nearsighted.